and took a try. So we notice that this starts in the upward position and it's colored in. And then this one moves 90 degrees to the right and the circle's still colored in. Then it makes a 90 degrees to the right again, making it downward. Then a 90 degrees again to the right, making it face to the left. And then after it makes a full rotation, we see that, okay, well, it goes up again. But this time the circle is open, makes another 90 degree, then another. So then we can assume by induction that our next figure is going to look like this. Again, not quite an artist, but I feel like all math teachers say that. So I'm going to give it another go here. Okay. Yeah, so it should look something like this. Hopefully yours is a little bit better than this one. But yeah, that's by using induction. We don't know for sure that it would be this, but based off of our previous figures in the sequence, we can assume that it will be this. Okay. All right, let me erase this. All right. So try this on your own. Please pause the video and try. Okay, again, your answer should be this. I'm going to try to do it full mode. It didn't quite work the last time, but I'll try. All right, so counterexample. So when proving a conjecture to be true, sometimes may be difficult. Sometimes it's simpler to prove that one is false. So to do so, all you need to do is find one specific example. Again, in reflection to what we are doing with inductive reasoning, and in adductive reasoning, we are looking at several specific examples and making a conclusion. When we're trying to make a counterexample, well, what we're doing is we're trying to disprove a conjecture. And remember, a conjecture is just an educated guess. So I am going to just come up with one example to prove that it's false. And if it is false, then I don't need to make several other examples, right? Because we already just proved that it is false. So when we're talking about counterexamples, it just takes one time of proving that it's false, and you don't need to make any other assumptions. So for example, if we look at the conjecture, a whole number greater than 10 can be divided by 3 with no remainder if the last two digits can be divided by 3 with no remainder. Definitely take a moment to try to come up with a counterexample on your own. Okay, hopefully you paused the video and tried. But let's look at one. Let's look at 169. 69 fulfills the requirements that two digits have to be able to be divided by 3 with no remainder. And so if we try to divide this, 169, we end up getting 56.3 repeating. So it is not divisible by 3. So this was a counterexample. So we know that the conjecture is false, and we do not need to come up with any more examples because we already proved that it is false. So let's try this. So a chord, you might remember this from your high school geometry. But a chord is a line that connects 2 points on a circle that does not cross the center of the circle. When you have a point on each side and it crosses the center of the circle, you get the diameter. So if you draw a chord connecting 2 points, it divides the circle into 2 sections. So if we look here, we have section 1 and section 2. If we just put 1 point, well, there's no other point for a line to connect. Thus, we don't get a chord, and we just have one section, which is the inside of the circle. So if we look here, it says, what conjecture can you make? If we look here and we have one where we have 3, well, if we count these, we have 1, 2, 3, 4. So we get 4 here. And if we look at the next circle that has 4 points, well, we get something that has 1, 2, 3, 4, 5, 6, 7, 8 sections. And then we have 5, where we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So here we have 16. So take a moment and think about what can we conclude the next one to be. If we're just looking at, so it's saying that if we have 6, what would we get here is what I'm asking. If we look at our pattern so far, well, we went, when you have 1 dot, you just have 1 section. When you have 2, you have 2. When you have 3, it doubles to 4. If you have 4, it doubles, it's 4 plus 4 to get 8. Then if we have 5, it's 8 plus 8 to get 16. So we can, just based off of here, by using induction, we can conclude that 6 should be 32. But let's see if that's actually true. So let's see if that holds up for 6. Try counting it on your own. So pause the video. And here, let's try. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. So we get 31 sections instead of 32. So our conjecture by using inductive reasoning is false. We would not get 32. We actually end up getting 31. So try this one on your own. Pause the video, please, and try it. Okay. These are the answers. Try this one on your own. And these are the answers. And let me actually explain this last one here. So when you go back and look at this, by deductive reasoning, what we're doing is we're trying, again, remember, inductive reasoning is we're taking a general statement and looking at what happens given a certain situation or scenario. So deductively, the problem says if we take any number, multiply it by 3, add 30, and then divide by 3, well, since both of these have factors of 3, we can take the factor of 3 out, and we get left with a plus 10. Yeah, just a plus 10. And then here, I think I'm missing something. Let's see, we have 3a, 3a plus 30. Okay, yeah. All right, and so, yeah, we get a plus 10 minus a. I forgot, you have to subtract the number that you selected from there. That's what I was missing. And the a should cancel, and then we end up being left with 10. So we know, without a doubt, as many times as we do this process here, we're always going to get 10. Okay. All right. And that concludes for this video. Again, I'll see you guys tomorrow in class. I really hope you guys have a great rest of your day with whatever you're doing. Again, the slides will be posted. I'll go over a lot of nuts and bolts stuff tomorrow in class. So, yeah, I'll be looking forward to you guys. See ya.